Okay. So this lecture has been uploaded to Avenue for those that would like to take notes during the lecture. And for those that were asking about the videos, like you'll find on Avenue for each lecture, I have already uploaded the previous ones. But as I mentioned last lecture, there are no promises. I would expect you to attend in person. But in case later on you want to revisit something or you're not able to make it to a lecture, this should be the exception. But yeah, again, I will do my best to put them in a timely manner. Before we start into today's lecture, I want to hear from you if you have any feedback about Lab 0. Most of you are already done. Today is the last session for the demos. I hope Lab 0 give you an introduction into what the board we are using and what we are doing with it, what is the setup, what is the IDE. Well, Lab 0 is just an introduction. That's why we call it Lab 0, not Lab 1. So the fun didn't start yet. But again, I would like to hear if you have any feedback about that. How did it go? Was it okay? Was it reasonable? Was it too easy? Good review. Okay, good. So all the concepts there you guys have done before. Like this is what I kind of take the word review as, right? So it's not a new concept, but it's more like a ramping up introduction into what you have done, and let's really put it into the context with the board we have. Good. So this is exactly what was Lab 0 about. So it's good that you see it the same way. Is there any other feedback? By now, all of you have groups, right? You will continue with that group to the end of the semester. You will do the labs and the projects related to the course together. So this settled down as well. I would assume so. Okay. So as we have done in the previous lecture, so again, what is the bigger context here? So we started with the introduction and what is this course about, and then we started with the top layer, which is software, revisiting some of the C, syntax, pointers, and some of the context of software embedded systems in general. And this aligns pretty well also with Lab 0, where we focus mainly on revisiting pointer structures and then how to use them into writing the driver at the end. Then today we're going to pick another layer. This is basically the style of the course, is that we have the full system layers in the first lecture, and every lecture we visit one of those layers. Maybe some layers will take from us multiple lectures, but the concept is, well, this is the layer we're focusing on. Let's really learn a little bit about it in the lecture, revisit some of the concepts, add some new, and then you go to the lab and then you integrate it with the system as far as we can, right? So we develop together towards the full system picture that we will have at the end. Good. So today's layer is the I/O interface layer. And this aligns pretty well with the lab starting next week, Lab 1, because Lab 1 is mainly about starting the motor with the EC and how to use some of the I/Os there to, well, send some data through the UART and how to interface the radios, etc. And all of this is done through IOs, right? So what are IOs? Again, most of the concepts you have already covered in 2DX or similar courses, but we'll try to revisit and put into the context. Good. So if we start from the general purpose computing, not embedded system world, we are already aware of some of the IO devices, right? So you guys know that, well, if you have a mouse in your desktop, this is in fact an input device. If you have a screen, this is an output device. If you have a keyboard, that's an input device. So we already know you cannot really interact with your own computing system without input-output devices, right? So the input-output device is the gate, is the interface between the computing world and the physical world, right? If you remember the theme of distinction between embedded systems and general purpose in the first lecture, we said one big difference is that embedded systems interact more and more with the physical world, right? So that means we have much more input-output devices. So if we had only these few, well, printers, monitors, mouse, keyboard, disks can be considered as an I/O. Well, by the way, how disks are I/Os? You don't interact with the disk physically yourself, right? You have the disk inside your laptop or your desktop. So why we have disk here as an I/O? Yeah, exactly. Thank you. So a disk is not, in fact, integrated into the CPU chip, right? It's something external to it. And to be able to write to the disk or read from the disk, you have, well, the CPU, the instruction set, the hardware underneath should send, like, write to some registers, read from some registers exactly as it deals with a monitor or a keyboard or a mouse. And for that reason, disks are very, very slow, right? They are in thousands of cycles compared to 100 cycles of a main memory, for example, right? So one reason why disks are too slow is because, well, the way they are interfaced to the CPU, they are very external to that, right? Well, the nature of the operation of the disk, which is originally magnetic, and now we have some of those SSD or non-volatile memory disks. They are much faster because of the technology, but they are still input-output devices, and this is one of the bottlenecks. Good. But as I said, if we go to the embedded system world, well, it's completely different, right? We no longer have couple, 3, 4 input-output devices because embedded systems, by definition, need to deal with the physical world, right? So to be able to do this, you have to interact a lot with the physical world. If you remember the 4 steps we have in a cyber physical system, you need to sense first, and then communicate the data to the processing element, do the processing, and then actuate. Sensing, well, these are sensors, but sensors are external to the CPU or the microcontroller that is really handling this. So you have to deal with sensors as IOs. And then at the end, actuation means change the physical world. This usually also happens through IO devices like motors, for example, as you see in lab 1, right? So in lab 1, what you will do is you will read data from the IMU, from the gyroscope, for example. So this is the sensor, but this sensor is interfaced through an IO protocol that in a couple of slides we'll discuss some of them. And then when you actuate, when you change the speed of the physical of the motor, then you also need to, well, write into an IO device. Here we have a bunch of those. Some of you might already aware of some of those IO devices. Does anyone identify any of the IO devices you guys have dealt with before or you are aware of? Any name of something we have here? Yeah. So can you raise it? Which one? Third one from the left. Okay. This one? Okay, what is that? Yeah, it's the Wii controller. Thank you. Yeah. Ultrasonic sensor. Thank you so much. And this one we have in the last lab. Others, are you able to identify any other IO device? Yep. Servo motors. Servo motor, exactly. Thank you. And we are dealing with this in the coming lab as well, if I remember correctly. Yeah. Others? Yeah. Well, we have the motor here, right? That's an actual motor, right? That you guys also deal with in lab 1. Those arms, you can imagine that they need, well, there is a controller here. You're able to see my mouse, right? Yeah. So those arms here. Okay, that's good. I guess that's because of the sharing. So anyway, okay, so basically this is more or less like a controller. So it's a keypad where you can send things. We have one similar to this, or in fact achieves the same function as the Wii controller, which is our radio controller. We have a one that is in fact quite advanced that we also use to drive the car. Do we do this in lab 1 as well? Lab 2, I believe. Yeah, we do this in lab 2. And the same thing here. If you have anything with an arm, then you also need a servo because you need to change the direction. And then you need a motor to basically control the speed. What else? Yeah, we have. Well, can you mention something that maybe is not here? Like some very popular I/O devices in embedded systems right now. Yeah. Gyroscope. Yeah, which is more like a sensor, not an actuator. That's correct. Yeah. Others? Most of these here are, yeah, well, they are a mix of sensors and actuators because they have the ultrasonic as well. Yeah. LED. Yeah, LED as an output. That's correct. This is what you have in Lab 0. There are cameras as well, which can be considered as an input device, very common in autonomous systems right now. We have leaders, right, as also very common in autonomous systems. Okay, so this is the reason why we need it back, and not completely, not just for the pen. It's too bad. So this is the reason why we need like I/O devices and different protocols, because we have very rich, well, sensors, actuators, and in fact, next lecture is dedicated to sensors, actuators. So we will cover this more. Let's see, what should I do? For some reason, you see things that I don't see on my tablet. Okay, so it's from here. Okay, all good. So as I said, like next lecture is focusing mainly in some of those sensors, actuators, and how they, well, some of their specifics or details and how to approach their data sheets. But today's lecture is mainly about the I/O technology itself, the one that is enabling sensors and actuators. So as you might already know from before, for the CPU to interact with an I/O device, now I'll call sensors and actuators I/O device. So I'll abstract that, right? Because in fact, some devices can be both input and output. Some is only input, some is only output. And it doesn't matter if you try to abstract, and regardless of the specifics of any of these sensors and actuators, they operate exactly the same way, more or less. So we're going to abstract the concept. We have a CPU, a processing element, that's the intelligent part of your whole microcontroller, and you want to interface into I/O devices. So the way this is being done is we have two types of buses. We have an internal bus and an external bus. So the internal bus is the one that is connecting the CPU to the memory and to what we call I/O controllers. Good. And the external bus is the one that is really going out of the I/O controller to the different input-output devices. Good. Some examples of internal buses, which is, well, there is the North Bridge from Intel, there is AXI from ARM, which is very common, there is TileLink for RISC-V. And then examples of external buses, well, these are the ones that you know more, right? And there's a GPIO, that's Lab 0, there is a UART, USB, I2C, SPI, CAN, Ethernet. You can think of all the possible interconnect in embedded system as an external bus. Good. So how do we talk as a CPU? Like how does the CPU talk to the I/O device? Well, the concept is pretty simple. The CPU sees the I/O devices as if they are only memory, right? And this is how you really enable programming them the same way exactly you write any normal C program, right? So you have already seen this in the Lab 0 through the GPIO LED programming the driver. But what you do is you need to configure few registers to tell the I/O device what to do. And then if you want to communicate something to an output device, like the LED, for example, in Lab 0, you write to a register. And if you want to read data from a sensor, for example, you read from a register. Those registers are not actual physical registers that exist in the CPU, but they are rather memory locations, right? So why the CPU, from the technology perspective, the concept is you want to map the I/O devices as if they are memory locations, right? Because doing so, you can think of all the programming languages we have. We have what we call the Van Neumann model, right? This is the model where you only have computation instructions and memory instructions. How to deal with the I/O devices? Well, those are memories. So you load something to a memory or you store something from the memory. Good. This is what we mean by memory mapped. Means every single I/O device would have a register in a specific address in the memory that the CPU interact with. If I want to write into it, communicate some data to it, I'm going to store into that memory location. If I want to read from it, I'm going to load from that memory location. Good. This is what I was saying. This part of the physical memory is mapped to hardware controllers, or the peripherals, the I/O devices, and then reading or writing from those memory locations allows the CPU to interact with the I/O devices. Good. So if we talk about memory mapped or internal bus, so simply the CPU, so here in that part, you might imagine that the CPU is attached to the bus. Okay. And then that's the internal bus in your system, in your microcontroller, for example, in our FMU66. And then you send to the, well, there is an address decoder because you send an address to that register. And then there is a control circuitry that is able to, well, this is exactly what you interact with. This is what you have done in Lab 0. You wrote into configuration, status, controller registers to do a specific task for this I/O device. Good. In our FMU, if I go, that might not be very visible to you, but if you open the data sheet, you will find where are the peripherals mapped in your memory. And I would assume you had to do this to be able to program the LEDs in Lab 0, right? So if you open this table, which is table 5.2 in the data sheet, you will find that the port A registers, which is your multiplexing control, which tells you whether you want it to be an input or output or a GPIO in general, then these are the addresses you have to interact with. So if you write a driver, if you are like an embedded software engineer, which is what you have done in Lab 0 for the LEDs, then you need to know where are these addresses and you need to write your driver in a way to write into them and interact with them. Good. And then this basically every port has a memory portion. The first address is the address of that port, but then inside the port, there are multiple registers. As we said, there are status registers, control registers or configuration registers, there are read registers and write registers, right? So another table, which is the GPIO memory map table, gives you the specifics or the details of how you can interact with this port and what are the addresses of the registers you want to write to. Good. I will assume also you have done something very similar for the TI board you have done in the 2DX, right? Because there is no way you can really write to an actual input-output device without knowing it, unless you have been using an actually already given like libraries for you to deal with the drivers, right? Which we'll try to avoid as much as we can in that lab to give you a chance to interact with the real world. Here I'm showing you the example we have done in Lab 0. You needed to read the data sheet basically to come up with the uses of each GPIO register and figure out what is the memory location to be able to deal with them. So hopefully by now you already know what is a memory mapped IO. I would assume, again, you have already done it, at least in Lab 0 and most probably before. So this was only a revisiting information or putting it all into context. Is there any question on that? Does this make sense now? Let's help illustrate what you have already done in a theoretical basis. Okay, good. So now going to the external bus. So writing to those registers. So it's a two-step process. The first step is through your software, you ask the CPU to send load store instructions into your IO controller. So this happens through the internal bus, right? But configuring this is not enough, right? There is something that must also happen, which goes through the external bus. So there is a controller that resides in the actual chip, the FMU SoC itself. But then you need to interact with the physical world. For example, if you connected the radio or if you connected the wireless connection to be able to interact with your laptop, which you will do in Lab 1, in that case, this is an external connection, right? So it has to happen through one of the external common embedded protocols, right? Here I'm giving you a bunch of names. I would assume you are aware of at least a couple, 3 of them. UART might be the most common. GPIO, what we have done in Lab 0. There is USB, I2C, SPI, and through the rest of the lecture, we're going to cover the details of some of them. Maybe one question to you, and again, I'm learning from you what you have covered before. Did you guys cover any of these protocols in a detail? So how they work, how they operate in a previous course? Yes or no? And I2C, like how I2C really operates. Is this in 2DX? Okay, good. Good, thank you. So again, connecting this to what we do, if I look into the block diagram of our chip, then you will find in the core of the chip, there is the actual ARM processor, right? That's the Kinetics P66, which is an ARM M4 processor. Good. And then this actual chip processor is connected to the interfaces, the boards, the actual things you put into your FMU wide package through an I2C. And then there is a UART here. There is an SPI. This is the GPIO that connects to the LEDs you have done. There is a CAN bus as well, because this FMU can also be used in automotive applications. So CAN is a very common interconnect protocol for automotive. There is a new automotive protocol, which is called Ethernet 5 or Ethernet 2. So it's a 2-wire Ethernet. And this is one of the active interconnect protocols that people are trying to replace CAN with because it's more secure but still under investigation. So CAN is still the dominant part. But there is a bunch of protocols. So, and there's something very good about, well, when you choose, for example, an MCU for your own application, if you want your application to be generic, you want to choose a device that allows you to interact with it in different protocols. Why that's the case? Because every protocol has its own advantage and disadvantage, as we will see later on. So there is no dominant protocol. So maybe someone can ask why we have all these protocols. Why it's not standard? Only one protocol at like for all applications, right? But it doesn't work that way because every application has its own constraints and requirements, and hence it requires a different protocol. Okay? So this is another way of looking into it from the low level. The only thing that is different here is it tells you, in fact, what is the part component that they use inside the SoC to enable that protocol, right? Good. So let's go through them one by one, hopefully quickly. And then we try to see the rationale of why we have multiple, what are the advantages and disadvantages. The very first one and the easiest one is the general purpose I/O. And in fact, that's also the one that is most common. So if you get any microcontroller, regardless of who is the vendor, you will have to find the GPIO, because this is usually what people interact with for educational purposes. Like something that is general, you can configure at either input or output, and usually is connected to LEDs for illustration, right? So GPIO refers to programmable digital input-output bins. The way you can program them as an input and as an output is through, in fact, having a tri-state buffer that really configures the port either in that direction or that direction. It uses voltage levels to represent signals. So 5 volt means logic 1, 0 means logic 0. And it's very useful to interact with generic input-output devices. So if we have the example you have done in lab 0, again, assume a GPIO bin can draw up to an 18 milliampere current, okay? And you want the LED, if it's on, then, well, if you look into the LED, it tells you that it has a voltage drop of 2 voltages. Then if you try to calculate the resistor that you want to connect to your own LED, then you just apply Ohm's law from high school, and then you end up with the resistor value that you want to attach to the LED, right? This is probably, if anyone in high school had an Arduino for the very first time, usually they ask you to put an LED with a resistor and then a potentiometer, and then you keep switching the potentiometer to determine how the LED intensity is, right? That's one of the very simple experiments we teach for high school students. The reason this is happening is because by changing the resistor, you change simply the voltage drop across the resistor, and hence the intensity of the intensity of the LED that is driven by the Arduino in that case. Taking this to our own board, then if you look into the schematic and try to extract the part that really deals with the LEDs, well, it's very similar to this textbook picture, right? So you have here a board that is connected to the red LED. Well, it goes through some register, some resistors. The values are different because the current values and the voltages that are driven by the MCU are different. But at the end, you have a drive transistor that really either, well, can do this as an input or an output. In the case of the LED, you always feed output to the output current to the LED. Good. Okay, so given that we mentioned GPIO as a general input-output device, which is the easiest, might be even a dumb information for you, but let's abstract a little bit something theoretical. So regardless of the protocol you are using, there are different technologies or different categories of protocols, right? And we'll try to categorize them. Well, first thing is there is serial versus parallel, right? Serial communication is, well, from the name, is just sequential bits. You have a single wire that you keep sending bits through, right? Well, why I might have that? Why I don't have multiple wires and then keep sending all the bits in parallel? What do you think might be the advantage of a serial communication? Yep. Yeah, you mentioned a very good point, and in fact, well, it's good that you started that. So you mentioned if you are not very worried about bandwidth, maybe serial communication is your best choice because you save wires, right? And maybe you save power as well. But does it mean that serial communication always has less bandwidth compared to parallel communication? Might not be true all times, right? Correct? Because maybe even serial communication with using one wire, it can still be faster than parallel communication. Is that possible? Why do you think this might be the case? This is more or less trying to apply your electronics courses then, right? If you have multiple parallel wires together, they will interfere with each other, right? Through ISI and interference of the signals, right? So they are very hard to maintain, which means if you operate in a very high speed, this, intersymbol interference will increase, and hence you will have signal distortion and noise. So in fact, parallel protocols cannot operate in very high speeds with that purpose, right? On the other hand, if I have a single wire, Well, as far as I can send data in a certain rate to my single wire, there is no interference across that wire, so it can be fast, right? So there are two factors that in fact control the bandwidth: the speed of the transmission, which we said maybe serial can be better on, but also the rate of the transmission, where in the parallel, even if you operate in a lower speed, I'm able to send multiple bits at a time. So it's not really a winning specification to either parallel or serial. It depends on what is the rate you are sending through and how fast you can really run your parallel bus, right? This makes sense. So you have always to think as engineers, and you guys are graduating, what are the trade-offs? Because in 99% of the cases in engineering, there is no one clear winning approach, right? It's always that they have to make trade-offs and choose you make your judgment, and then you choose the best solution to your own specific problem, right? That's really the engineering art there. Good. As we said, parallel communication, I can send just multiple lines. We have already discussed some of the advantages. Why? I've already discussed some of the advantages, disadvantages. But can you, before we go to the next slide, can you think of some of the protocols you have already used and whether they are serial or parallel? We have already mentioned I2C, SPI, UART, USB. What do you think? Which one is serial and which one is parallel? You said, for example, you covered I2C before. Is that a parallel protocol or a serial protocol? Serial, yeah, that's correct. Yeah. What about UART? Yeah. Serial protocol, yeah, correct. So you can see that most of the things you have already used are serial, right? Not parallel. What might be the reason? Yeah. Can you think? We mentioned examples about like distortion and interference. Can you think of any other reason? Yeah. Easier to implement. That's correct. Yeah. Is there another reason? Yeah, more common in industry, but we're trying to ask why it's more common. Yeah, but it's correct. It's more common. Yeah. Yeah, easier to implement / cheaper, because always in engineering budgeting, you think of easier as lower cost. Easier doesn't mean that the engineer will not suffer, right? This is something that you also have to pay attention to. When people say easier, they don't mean that you don't spend a lot of time and days and nights implementing it. This really doesn't matter. What matters is how many days and how many engineers you need there, and you factor this as a cost. And then if it's lower cost, that means easier. So it's yeah, you are correct, but it's just another reflection of being easier to implement. Yeah. Okay, good. So we'll come into that in a second. You were correct that basically I2C is serial, UART is, we'll come into UART. But one of the fundamental, in fact, the first serial interface with the RS-232. Have you ever interacted in your life with an RS-232? I don't think you are old enough to have seen even a desktop with an RS-232 board there, right? Have you seen that? Has anyone seen that in a desktop? Because these were very common. In fact, well, on my high school days, the only way to connect a keyboard and a mouse to an actual box was this RS-232, right? And monitors, well, monitors were using something different. I will come into it in a second. Okay, good. So this is basically the RS-232. That's the parent or the father of all the serial protocols, right? You don't see it nowadays because USB, well, is just the winning approach right now, right? But all of the protocols that came afterwards, especially the USB, is in fact building on top of the technology of RS-232. For those that are like hobbyists for electronics, you will find a lot of circuits that does the translation between RS-232 and USB or RS-232 and UART as well. You can interact with RS-232 chip through UART. I2C and SPI we will deal with the most, so we'll cover those. But there's also SATA. Do you know where SATA is being used or have been used? Yeah, hard drives, exactly. So this is the old hard drive, especially the mechanical one. They were SATA. What about parallel interfaces? I will ask the same question again, and maybe this is, well, it's an older protocol. So have you ever seen a desktop with a barrel board? You have seen that? Okay, because those ones kind of got extinct before even the serial board. So this was also very common in desktops before. There is the PCI. So among the barrel interfaces. So and this is the lesson that we're trying to learn here. So we have covered some of the serial protocols and the barrel ones. From what you see is the ones that are aware with, the ones we are using nowadays are more serial, right? For the external bus, right? Which, because we are only talking about external buses now, right? We didn't give any examples of what is internal, which means between the CPU and the I/O controller, right? For the external buses, it seems that serial is more common, right? So this is basically one important lesson. Why that's the case? Again, you mentioned few examples, and we'll cover some more examples. But among the parallel interfaces, do you know which ones is currently being still very, very common nowadays? Yeah, someone else? Yeah. PCI, exactly. PCIe Express. It's PCIe basically. If you look into what is already there now, it's not really the PCI, but it's rather a PCIe, which is an advanced version of PCI that in fact tried to combine benefits of parallel and serial interface. But that's the only one that you think in fact is very common, especially for networking stuff. Good. So now for the discussion back again to advantages, why serial interfaces are very common for external buses. Well, parallel interfaces derive better performance for the same clock speed. So the discussion I had with your friend earlier is when you think about bandwidth, there are two factors to think of. Okay, so if you think about bandwidth, you have to think about the rate of transmission, right? Which is your clock speed. And sorry, you have to think of your clock speed, which is the frequency you are transmitting through, and the rate of the transmission, which is per one clock, how many bits you transfer, right? For parallel, if I'm fixing the clock speed for parallel and serial, definitely parallel is better, right? Because I'm sending more bits at a cycle. So my overall bandwidth or performance will be better. The problem is I cannot take this further to increase the clock speed. The reason is synchronization is very tough for especially at high speeds. I already mentioned to you because of the distortion and the interference and the noise on the wires. So this is why parallel buses cannot operate in a very high speed. And that's one reason why, in fact, serial communication is very common for external buses nowadays. On the other hand, synchronization inside the chip itself. So we had external bus and the internal bus. So well, go back to that. Okay, I would promise I will not use the pen again today, but please come back. Okay, so let me see. Yes. Okay. So we mentioned that serial protocols are very common in external because of the problems we mentioned, the speed, etc. But if synchronization and distortion is the largest problem for parallel protocols for external buses, this problem is less severe for internal buses because inside the chip, you have better control, you run in a much smaller area, and also you can run in much higher speed. So in that case, synchronization, because you can drive only one clock tree, synchronization is much easier. And for that reason, parallel protocols, we just go back to the slide we were in. Parallel protocols are dominant in internal connection. So if you think of the most common interconnect protocol used nowadays for systems on a chip, AXI is the one that is winning. And again, as I mentioned, there is tile link from RISC-V, but both are in fact parallel buses, right? So they are 64-bit wide, or at least they can be even more. So they are parallel buses. The reason is I don't have these problems, or I have them in a less severe manner inside the chip. And because inside the chip, I want to run in a very high speed, and I also want to maintain very high bandwidth, then parallel interfaces or parallel protocols are the ones that can be used. Good. So the lesson is, or the conclusion is, serial protocols are very common for external buses, while parallel protocols are very common in internal buses. Good. Then another classification is whether you have synchronous interface or asynchronous interface, or you have a synchronous bus or asynchronous bus. So what we mean by this, synchronous communication means both the sender and the receiver, the both sides of the communication must be driven by one clock. So you run at the same clock speed. Why this might be wanted, why this is an advantage? Because if you run in the same clock speed, then you don't need really to synchronize, right? So if I'm sending you something, for example, I tell you, I send you a command after X cycles, let's say 10 cycles, I'm expecting the data. You don't need to tell me when the data is ready. Well, I am ready. Are you ready? Yes, I'm ready. So the three-way handshaking is not needed there, right? So synchronous communication is in fact much easier to handle from the protocol perspective. What is the problem with synchronous protocols? Again, synchronization is not easy to maintain because you have to drive the same clock. They must be completely aligned to be able to operate correctly, right? This alignment is hard to achieve. In fact, in unrelated matter, if we talk about modern DRAMs, DDR4, DDR5, etc., one of the basic problems that is preventing them from really achieving higher speeds is this synchronization that is needed between the off-chip memory, the DRAM, and the actual CPU, right? So this is a fundamental problem that is being faced there because DRAM is a synchronous memory. It's called SDRAM, synchronous DRAM, right? So which means it's driven by the same clock speed as the memory controller on the chip. All parallel communications are synchronous. Maybe one question, why that's the case? Why parallel communications must be synchronous? What do you think? You guys have to think of things are not, so I guess we are beyond in fourth year, we are beyond that there is a piece of information already in a textbook taken for granted, right? Later on, you will learn when you go to industry or even academia that there is nothing is for granted, right? So why? Yeah. Yes, that's a good starting point. Why I wouldn't know when to sample the data. Yeah. Yeah, so what you said first is correct, but the subsequent argument is a little bit not true. So think of what happens in a serial bus, right? So in a serial bus, in UART, for example, what do? You need to send, well, this is my start, keep sending data, this is my end, correct? This is okay for a serial communication because it's serial, which means the start bit definitely will arrive first, right? In a parallel bus, how can you choose one wire to be the start? It makes no sense because all will arrive at the same time. So you will not know when to sample, but not because of the running speed, but because of the nature of parallel communication itself, right? So all the bits arrive together. How do I know that? Well, if one of the wires is the start, then what can I do? The only way to do this is you waste a whole bunch of bits at the beginning. Let's say if your bus is 64-bit, you say my very first 64 bits are only for establishing the communication. It's a waste, right? That's why no one really does that. Good. And that's, as we said, it's one reason why parallel communication is problematic for external buses because of that synchronization issue. What about asynchronous communication? There is no requirement for running in a shared clock, which means you can operate in different speeds. Like in the UART experiment you'll be doing in lab 1, well, we are running from our own desktops or laptops, which runs in gigahertz, to the FMU, which is running in few megahertz. And then we are establishing the UART connection between both, right? So sender receiver are running in different speeds, but the UART is able to handle them. The way this is being done is through the start-stop. Well, I don't want to use the pen, but that's through the start-stop, right? Which is, I establish the connection right now. Sometimes it's referred to as three-way handshaking or two-way handshaking. It depends on the protocol. And also in the agreed upon speed that you are thinking of. So in the UART, for example, you set your baud rate, right? Because I've done this in 2DX, which means now I'm establishing a communication with that rate. So both sender and receiver agree on the rate, and hence they expect the data to come in that rate. The problem with this non-synchronous way of communication is because of the handshaking, it has high overhead. If you think about UART packet, for example, if it's only 8-bit, you need to send a start and end, which means you waste 2 bits out of 10. So 20% of your communication is just an overhead. So this is a disadvantage there. The very first example of asynchronous communication was the RS-232. You need basically, again, to do the start. Use the pen. So that's the start, and then you send your data, and then you do the stop. In UART, it's again another asynchronous protocol. In fact, UART refers to Universal Asynchronous Receiver Transmitter. The circuitry is a bit advanced, so it can be interfaced to RS-232 or any other serial bus, because it can be configured to operate with different protocols. As I said, it can interface to RS-232, USB, or any other thing. The reason is you establish your own configuration of the communication as part of the protocol. What is your baud rate and how to configure the communication? For example, you want it to be 8-bit or 16-bit. For the UART to be able to operate, you need at least a TX and RX lines to function, right? So you need, if you look into the UART protocol here, let me see how to identify the TX and RX. It's not very visible to me. Yeah, here there is a RX ready, TX ready. That's an out. This is the in. Why is that small? Yeah, and the important part is because you want to operate on a low, well, in a particular speed, you need buffers, right? So this is very common also in asynchronous communication, is you need buffers because the data arrives in a non-synchronized way. So sender might be sending data while the receiver is not ready. So what would happen is you will buffer that data into either a TX RX buffer, and then later on you will consume it. Yeah, the baud rate again is the sender and receiver agree upon transmission speed, which means how many bits you send per second or how many bits per cycle. And once the receiver detects the start bit, it knows that the sender is going to send with that rate, and then I sample 8 bits back to back before I receive the stop bit. So the way we do this in lab 1 is you will interface, as we said, we'll interface with our laptop terminal. So you will write something, you write a command in the terminal in your desktop or laptop, and this command will be sent over a UART communication to, in fact, this transmitter, which is a wireless transmitter. So we'll have 2 of these transmitters. One is attached to your desktop, another one is attached to the FMU itself. The one that is attached to the desktop, it's a USB connection, which means you deal with it in a UART fashion. So through the command, you will set up your baud rate. The data transmitted will be sent to the wireless transmitter that is attached to the USB of the desktop. And then the wireless transmitter will send it to the wireless receiver. And then the wireless receiver will send it through UART to the actual FMU, right? So we're using UART in both sides, but the connection in between is wireless. Good. And for that reason, you will find this function in lab 1, which is setting up the UART, right? So if you look into, you're able to see that, might be a bit small, but if you look into this, you need to set up the baud rate. Here it's set to 57600. You enable the transmission side true, the receiver is true, which we said this is the least thing that is required. And you enable some other things that you'll discuss more in the lab, and then you initialize the UART, right? So this is your initialization function that sets the UART configuration. Good. Okay, so we have discussed serial versus parallel communication, synchronous versus asynchronous. And then there is another way of classification, which is point-to-point versus shared bus. What does point-to-point mean? Assume you have multiple input-output devices and multiple processors. Good. So you have multiple senders and receivers. I either have the choice of to say I set a common bus between all of them, and then they will communicate through this common bus. Or I would say every single sender or receiver is directly connected to every single sender and receiver. The latter one is called point-to-point, which means everyone is connected to everyone through a mesh network. Good. On the other hand, a bus is just shared. Well, what is the advantage of point-to-point? What do you think? Why point-to-point might be useful? Yep. Yeah, direct communication, no interference at all, no delays, right? So assume all of them want to talk to all of them at the same time. That's possible in point-to-point because you have a dedicated bus. It's like saying you have 10 cities in your province and there is a separate highway between every single 2 combinations of the cities. In that case, traffic is expected to be much less, right? Because there is no, if someone wants to go from city A to B and then C to D, another one from C to D, they will never interfere. But there's a dedicated bus, right? On the other hand, shared bus is not the case. It's only one highway that everyone has to go through between all the 10 cities, right? Well, you can expect the congestion to be much higher in that case. So, well, this kind of favoring point-to-point. So what might be the disadvantage of point-to-point or the advantage of bus? Yeah. What do you think? So in a point-to-point, this is an interconnect that is very high costly, right? And it consumes a lot of power because you have to have wires everywhere. So routing also would be a problem. Think of the highway example I gave. Well, establishing those highways is very costly, right? Going to eat up a lot of tax money, right? And they might not be utilized. So underutilization can also be a factor there, right? Is it really true that everyone want to go and talk to every other one in the system simultaneously? Well, might not be the case. So why you design your system for the worst case? Good. So this is why, in fact, in most of the current approaches or the current SoCs, shared buses are the common one. I give you the example of AXI or TileLink. Those are shared buses, right? So in the shared bus communication, a master, well, someone that wants to initiate a communication, and there is the concept of very interesting sound. We're not going to explore. Hopefully we're good. So a master is the one that wants to establish a connection, regardless of whether this is a CPU or an IO, it doesn't really matter, but someone that wants to initiate a connection. A slave is the one that really want to consume, well, this is the target of this communication. And the same, one entity can be both master and slave, good? Regardless of the terminology, I mean, people are going away from master-slave language now, but it doesn't really matter. The concept is what matters us as engineers. The idea is someone want to initiate a communication, can call it initiator if you would like, and this communication need to go to a destination. This is basically the other entity, good? I can be on the same time a master of one transaction and the slave of another transaction. So I can be the initiator. I want to send data to one of the IO devices, one of the actuators, for example, while on the same time, a sensor want to send me data. Okay? In most embedded systems, CPUs are really the dedicated masters, which means the ones that are able to establish connection. Why people do this in embedded systems? Because you don't want your IO devices to pollute or bottleneck or make a denial of service for your CPU. So a CPU is the one that is saying, I synchronize all of this. When I read data from you, I'm going to check it. You only interrupt me if you want, but I respond to this interrupt based on my own needs, right? So the CPU is the one that is handling all the communications. So, well, this was the third category we have done. So we have done parallel versus serial, synchronous, asynchronous, and point-to-point versus shared bus. Going back to the protocols, we have discussed UART and RS-232, or the serial in general. Then the third one that is common in serial, and you guys have already mentioned, you have discussed, is I2C, right? I2C is developed by NXP, which is ironically is the one that we have the board from. And it's basically asynchronous, well, don't use them, it's synchronous serial communication protocol, which means it has a common clock between the sender and the receiver. And it uses two wires, which is the clock and the data. So you only have two wires. Your clock, because it's a synchronous protocol, and the data itself, it's a single wire data because it's serial protocol. The problem with I2C is a couple problems. The first one is it only has 7 bits for ITs, so which means for any I2C bus, you can only attach a maximum of 127 devices, right? So if you have a very big system, I2C might not be very common. Sometimes people get across this by writing by having a hierarchical architecture, but it becomes a bottleneck problem. So they go away from I2C if you need a scalable system. Good. The second problem is half doublets because you have a single wire, so you don't have transmitter receiver. So you either is transmitting or receiving at a time, which means it runs in low speed, right? Its bandwidth is small. To address this specific problem, we have another protocol, which is SPI. SPI is a serial peripheral interface. This has been developed by Motorola, which is one day was one of the big Silicon Valley companies. Nowadays, you don't hear about them. But synchronous serial communication protocol, the main advantage of SPI over I2C is it uses two wires instead of one for data. So you have a sender and receiver, which means it's full duplex, right? And because you have sender and receiver, it uses what we call 4 lines. So you have, well, I wouldn't go through the actual bits because you will do this already when you go through the data sheet of the lab one. But because it's synchronous, you don't need stop bits. Its limitation is you can have a single master, multiple slave, which means you can target multiple destinations at the same time, and it's very good for speed. Right? Doesn't mean that SPI is always winning over I2C, right? Why that's the case? Because we increased the wires from 2 to 4. This might be okay if you have a short distance communication, but if you want something that is long distance, this wire becomes costly right now, and the interference will increase, noise will increase, and the data integrity will decrease. So in that case, SPI is not good for long distance communication. People prefer I2C on that hand. Good? Does this make sense? So the main focus is to understand the trade-offs between different protocols, and we'll be using all of them in our lab. If I go to what our actual board, looking into the schematic, you will be able to identify, well, you will be able to see, but that's a screenshot from the data sheet where you can identify the SPI 4 wires. In fact, if I remember correctly, FMU has 2 SPI connections, so you can identify SPI 1 and SPI 2 4 wires that are coming out of your system on a chip. Good. Those are, well, if you don't see, you have to trust me, those are the lowest wires on the right side. So one reason I'm putting these screenshots in lectures is I'm encouraging you to really, well, the lab also asks you to do so. You have to go to the data sheet, start looking into the hardware when you write software, right? Because to be able to be a good embedded system engineer or have a considerable knowledge in embedded systems, you need to bridge the gap between software and hardware. This is the one then basically that is very common for us, regardless of what device you are talking about, whether it's mobile phone, laptop, tablet, it doesn't really matter. USB is one of the most common ones. It might be the most common serial protocol, in fact, we know nowadays, aside from embedded systems. You can have one host, multiple devices, which means I can form trees. Well, you cannot really form unlimited trees because if some of you have already tried this, building a USB bridge with multiple fan outs becomes a problem. But the general concept is applicable, so I can have a tree. The way that fundamentally the protocol operates is you use 2 wires for differential signal. Do you know what is differential signal is from electronics? What is a differential signal? I would assume you guys have at least taken one electronics course. Is that correct? Or no? Yeah. Okay. You didn't cover op amps or operational amplifiers at all? You did? Okay. So you cannot cover op amps without differential signals. So I would assume you had, but maybe you forgot over time. Yeah. You wanted to share something? Okay, good. So a differential signal is a very common approach in electronics in high speeds, because instead of using a single wire for the same bit of data, I'm using two. And it's very common in clocks, especially because clock is very sensitive. If you have a distorted clock, your system is done, right? So you'll find in many systems, clocks are differential. Differential means instead of saying I am currently sending one bit as one, which means interpret this bit as one, I'm going to send two wires. One has the actual value, the other one has the negated value. So it's 1 and 0, for example. Why I'm doing this? Because simply sending the same bit of data over two wires allows you to restore, even if there is a distortion, you can easily avoid the noise there, because the noise does not affect the wires similarly. So I can, even if in the existence of very high speed and very high noise, I can restore my original signal at the receiver side. Good. This is what we mean by differential signals. Two wires used for the same one bit of information in a negated way. Good. Usually you'll look into, if you look into any data sheet, you'll find clock and clock bar, for example, right? Bar is the negated part of the clock, and this is a differential clock. So by using a differential signal, USB is able to operate in very high speeds. If you think of even USB 3 is much higher as well. Good. Compared to the serial protocols, I mean. Good. So how to identify this differential signal? If you look into the table here of the USB, you'll find that you have a data minus and data plus, right? These are your two wires of the data. Good. And if you look into basically for the differential pair, the upper pair, which is data plus, if it's 0, D minus would be 1, 1, 0, 0, 1, right? So they are always kind of reverted. Assume for some reason your wire that is sending D plus is distorted. It covers, like it suffers from a noise. That means this signal will be reshaped a little bit, right? At the receiver side, I'm not only using this one, I'm also using the one beneath it. So any distortion that happens in one wire, it will be complemented by the extra information I have from the extra wire, which means I can restore my data at the receiver easily. Good. Okay, so we have discussed multiple considerations and few of the protocols in a very high level. Again, it's not the purpose of the course to dedicate one lecture to I2C and how it really operates in the circuit level, because by now it's very easy for you to go to a data sheet and read how it operates, right? And you would be doing this in the labs as well. But other considerations you might need to think of is, what about digital versus analog communication, right? Right now, it might be a very I would say easy argument to make that mostly we don't have any analog communication right now. This wasn't the case 15 years ago, right? In fact, it might not be the case 10 years from now, because especially in machine learning, people have found that analog can have very good effects compared to digital. Serial versus parallel, we have already covered. Wired versus wireless, right? I told you in lab 1, we have a mix of both, right? So we connect through the UR to our USB dongle that has the wireless communication. This is a wired communication, but then we communicate wirelessly from the sender to the receiver. It's a wireless communication, right? So whether you have your connection wired or wireless, this is another classification. You might think embedded systems are away from this, but in fact, not true in modern systems. Think of, you want to put a device in a river, basically with a sensor that measures the levels of contamination or something, right? And then you have multiple of those in a country, and then you have a centralized hub where you collect all the data, analyze it, and take real-time actions. Those must be wireless communication, right? I give you a very large scale project, but think on the other hand of what you want to have what they call implantable device inside a patient's skin, right? You cannot have it wired, right? You don't want the patient to keep walking with wires going out of their skin, right? That's scary. So you can use wireless communication there. In fact, short-term wireless communication or short-range wireless communication is very common in healthcare applications, right? So wireless is becoming more and more very common in embedded systems. That said, it brings challenges to the embedded system that didn't exist before, because wireless communication by nature is less reliable compared to wired communication, right? Because subject to distortion, hacking, and security issues, etc., etc. If you remember the example we gave about automotive, like locate and still lose it, right? The thing that you open or you use the wireless key for your car to open and close it, and then hackers can really intercept that. This is an example of a challenge in a wireless communication, right? If you have a physical key and the car does not have any wireless key, this vulnerability does not exist, right? It exists only because of the wireless communication. Another important factor you need to think of is what is the required throughput or latency in your system, right? We mentioned, for example, I2C versus SPI being full duplex versus half duplex. What latency am I looking for, and what speed I want to operate at. It might also allow you to choose between parallel and serial communication. Another important factor for embedded systems is real-time or quality of service guarantees. And this is a topic that is becoming more and more very common in systems on chip. And even in internal buses as well, not only external buses. I give you the AXI example from ARM as an example of a very common interconnect in systems on a chip. Originally, AXI didn't have any quality of service. First of all, do you know what is the quality of service? What are we referring to? So if you think of lecture 0, the one that we have covered the big picture, and I give you a few slides from industry, one of the requirements you have an embedded system is some applications want to maintain a certain guarantee, right? So I want to operate within this budget of time. I cannot exceed it, or I'm a soft real time, which means I need to maintain certain throughput. For example, your GPS, right? GPS is not really a strict hard real time, but we call it soft real time system, which means as far as you are maintaining a certain quality of service, you are good. If you are watching Netflix, streaming is also another example of a soft real time with quality of service requirements. As far as the rate is good enough for you as a user, if multiple packets drop, it's not a big deal. But once the rate starts going beyond a certain point, the quality of service degrades, and hence it affects the operation of the system, right? This is what we mean by quality of service. Most modern internal buses, and the most common one is the AXI, they have already added bits for quality of service, which means if I have multiple processors, I say this processor would require a quality of service with a rate of, I don't know, 10 gigabytes per second. This is 1 gigabyte per second, like 2 gigabytes per second. And then you change your hardware arbitration in real time to make sure you maintain all the quality of service of all the applications running on top of it. Okay. Power electrical requirements, this might be mainly related to the power consumption. So if you have, for example, parallel communication that you send so many bits, so many wires, it might drain your battery very fast. And reliability and security is another aspect there. I told you already people are trying to replace CAN with a more secure interconnect in a car, maybe Ethernet 2-wire, for security purposes. Good. Is there any question? Okay. So to summarize, so we have discussed, wow, this is finished very fast. That's good. So to summarize, we have memory mapped IOs devices. So this is the way that we abstract all the complexity of IO devices and how to deal with them into a CPU protocol. Like I map all my input output devices as registers in the memory, which means I can write legacy software to configure them, receive the data from them, or send data to them. Good. This is what we mean by memory mapped IOs. Every single peripheral. In fact, not all, by the way, this is something that's very important to mention. Not all IO devices are memory mapped, right? There are devices that are not memory mapped, but this is least common and they are very hard to deal with, right? Compared to memory mapped IO devices. Once you have a memory mapped IO, the CPU can read and write to or from based on reading or writing from these configuration registers in the memory. And then we have covered very quickly IO interfaces that we will interact with in the lab, including GPIO, UART, SPI, I2C, USB. And we have categorized them into multiple classes. Parallel versus serial, synchronous versus asynchronous, point-to-point versus shared bus, right? And we have kind of discovered that we have kind of discussed the trade-offs between every one and what might guide a choice for a certain system with certain requirements, which one to pick. Good. So by doing this, last time I owed you 15 minutes. I believe today I will owe you a little bit more. I know we don't also do breaks during the lecture. So maybe this is something I should ask you, given that we have time. Do you think it's better that we condense things and then we finish earlier, or we have a break in the middle, like 10 minutes break, and then you are able to consume the information we say very fast in the lecture? What do you prefer? Do you prefer a break? Just raise your hand. Okay. So you guys don't prefer a break and we condense and then we finish earlier? Yeah, okay. If you're able to comprehend, that's okay. But put in mind that up until now, I'm assuming 90% is a review, right? Maybe you change your mind. Maybe I should ask you later on once we go into the actual content that might be completely new for you. Okay? So say thanks everyone, and then I'll see you next week.